Hi everybody and welcome to the capstone project of this course. You are going to create and train a model capable of successfully segmenting lung cancer in CT images. As usual, let's talk about the background first. Lung cancer or bronchial carcinoma is one of the most common cancers and makes up to 25% of all cancer-related deaths. According to cancer.org, 1 in about 16 people will develop lung cancer in their lifetime. Therefore, lung tumor segmentation is a highly relevant task. Automation of this process offers two main advantages. First, it may help to reduce the false negative rate. In addition, it directly provides an initial size or volume estimate of the tumors. As the tumor volume is an important criterion at the tumor board, this automated segmentation simplifies the radiologist's life as he or she no longer has to segment the entire tumor but only make corrections. To tackle this task, you will use the lung tumor dataset provided by the Medical Segmentation Decathlon Challenge, consisting of 64 full-body CT scans with corresponding ground truth segmentation masks. Those scans yield 31,534 two-dimensional slices. The challenge of this task is the large scan compared to the relatively small tumor. Therefore, we have an imbalanced dataset. Let's take a look at an exemplar scan. You can see that the scan moves from bottom to top, and after around 50 slices the lungs become visible. A little bit later you can observe that this patient has a tumor in the right lung. Regarding the pre-processing phase, you could perform the following steps. At first, you crop away some region below the lungs, as we are only interested in primary lung cancer right now. Try cropping around 30 pixels along the last axis. Don't forget the segmentation mask. Next, you could try standardizing the scan or slice with a constant of 1 divided by 3071. Feel free to try using a lung window. When saving the individual pre-processed slices, please resize them to a smaller shape, as an example 256 squared, to drastically reduce the training time. Please make sure that OpenCV uses nearest neighbor interpolation. Otherwise, some pixels in the segmentation mask may have values between 0 and 1 as OpenCV interpolates them. Additionally, don't forget to create an appropriate train test split. You can find further information in the corresponding Jupyter notebook. If you implement your pre-processing in a similar way as we did in the last project, you can use the same dataset and model. However, regarding the training, we need to address the problem of data imbalance. To tackle this problem, you could use something called oversampling. Oversampling means that you compute the fraction f between tumorous and tumor-free slices to sample slices with a tumor f times more often. This may prevent the network from learning an all zeros solution. A sample implementation is provided in the training notebook. We observed good results when training the model for 30 epochs with the binary cross-entropy loss and the Adam optimizer with an initial learning rate of 1e-4. However, feel free to play around with all of those parameters if you want. Alright, now it's coding time. Please have fun tackling this project. If you get stuck somewhere, I highly encourage you to use the Q&A forum or simply ask on Discord. Of course, you can also find solutions for all tasks. However, please use them only as a last resort to maximize the learning effect. Thanks!